Okay, let's go and get started with today's lecture. In today's lecture, we're going to look at a little more stuff with objects in programming, Python specifically, and we're going to talk a little bit about one of the ways to design your code using an object-oriented technique called inheritance, where rather than recreating objects from scratch every time, you can essentially build an object design off of another object that you've already created. Now, first off, objects in Python. Everything in Python, unlike some other languages, everything in Python is some sort of an object. And if you look back at code you've written in Python, you can see that evidence of that show up. So for example, if you have a string like st equal hello, so just a string in double quotes there, that string itself has a .upper method that looks exactly like an object. So this string is actually an object. And in fact, you don't even need to put it in a variable. You could just say hello.upper, and it'll convert that to uppercase. So you have capital H-E-L-L-O, all of them caps, by just adding that .upper. And what that shows is this string of characters, that string sequence, the character sequence, is really stored internally in an object because it has a method associated with it. And there are other methods associated with it as well. There's .lower, there's .title. There's just tons of string methods that we can use to do things. So strings are objects. They have attributes. In the case of the sequence itself is stored in there, that data is stored in there, but it also has methods, object functions like .upper, .title, .trim, and so forth. Now, continuing on some other things that we've seen, we import a module, use module dot, and then the functions in that module show up as if they were a method of that module. So when we import modules, they get imported into kind of that module object that then has methods inside of it. So random.randint would be a good example. Math.cosine, math.sine. When you import modules, they get imported as an object. And even functions, if we just create a function like I have here, so def add 2, a comma b, result equal a plus b, return result. That's just a simple function, but it turns out that function itself is actually an object. And the name of the function is actually stored inside of that function. Excuse me. And in addition to that, name being stored inside of there, I'm trying to get away from that sun. In addition to the name being stored inside there, the code itself is actually stored inside it. And actually, let me switch over to Python here just for a second, and then show you what that results in. So let me go to a Python shell. All right, so here's a Python shell. So let me just define that function. So let's say def add 2, a comma b, and here we'll just say value equal a plus b, return value. So there's a function, and if I say take that function and say add 2 dot underscore underscore name, you'll notice that it stores that name inside of the function itself. So it knows its own name. The function has part of the object, knows the name of that function. And if I were to do, and we'll look at this later on, but if I were to say, what's the type of that function? Notice it's a function class. So there's a class for keeping track of functions in Python. So the add2 is an instance of a function type object. And notice that even though it looks like a function, behaves like a function, it's really just an object instance that has those things inside of it. And let's look at a couple of the other things that were shown in that slide there. So notice that underscore underscore code underscore underscore dot co underscore name. Let's try that. So let's do add 2 dot underscore underscore code underscore underscore dot co underscore name. So this is the name that's associated with that code, and you'll notice it's still add 2. And to continue along that same line, let's do the same thing. But this time, let's say, let's do CEO underscore code. And you'll notice that that's a string of kind of binary digits. So that's just a string of values. So this is actually this OR symbol, 0, 0, or 0, 1, or 1, 7, or not or there, 1, 7, 0, 0, close curly brace. So this is a string of just like what looks like junk characters to us. But what that is that's the actual code for this function as presented to the Python interpreter. The Python interpreter kind of tokenizes that code and sets up the code in a way that it can run very quickly. Let's also look at var names. So let's do the same thing, but let's do co underscore var names. This is a list of all the variables that are inside that function. So that's part of the object. So it knows it has an A variable, a B variable, and a value. And there you can see the A, there's the B, there's the value. All of those are stored inside of there. And it turns out there's a bunch of other stuff in there as well. We don't need to get into all of it, but it has a dictionary in there that has the values or the variable names and the values that are associated with them while the thing runs and so forth. There's a lot of stuff in there that low-level things that Python itself is using to do stuff that we could take a look at and mess around with if we wanted to. But the main point here is, going back to the slides, is that functions themselves are just a certain type of object. They have things inside there. The function dot has a name, has the code, it has the variables, it's got all the stuff that make the function do what it does, all stored inside of there, just like attributes or methods. All right, also numbers themselves. Like here I have a x equal -10. I can do x dot underscore underscore abs underscore underscore to take the absolute value and get 10 out of that. Or I could take this number 255 directly and do dot underscore underscore hex and give, that would give 0xff. So numbers themselves in Python are actually object instances of objects. And the type of those would be like an int type. And an int type is just another class. These are ints, but you might also have other types of number classes like floats. But the concept here, what I want to drive home, is that everything in Python is an object. Objects take a lot of different forms. Classes are actually themselves a type of instance. Numbers, modules, functions, strings, variables, everything. So let's take a little bit closer look at those to some extent. All right, so to start off here, objects all have the following. They have a type, like we saw earlier. Type was function, type is int. If we make our own thing like a bullet object, the type would be class bullet. So they all have a type, and that type determines kind of the attributes and the methods of that particular class of object or that type of object. So you can think of the type as being what class was this object created from, what blueprint was used to create it. They also have a value, that's the stuff of the object, and that would include the attributes and the methods. In other words, what makes it how it is. They also have a lifetime when we create an object instance, meaning how long is that object in existence. And an object instance also has a scope. In other words, where can we access it in the code? And there are 3 levels of scope in Python. Local, meaning like inside of a function. Global, meaning like outside of a function. And globally available. And built-in are ones that are part of Python. Things that are part of Python itself. Kind of like the print function. Okay, now objects in Python, if we think about what a variable is essentially just a name that gets associated with some object in memory. So if you create a variable like I, say I equal 100, that creates an object named I and binds that name to a particular object. And that object has, like all objects, a type, a value, a lifetime, and a scope. So behind the scenes, this variable I has the name I, it's a type int. It has a value of 100 in it right now. It's global scope if it was created outside of a function. And its application lifetime, meaning it'll exist in memory until the application terminates, or we delete it. We could delete it before that using del if we wanted to. And basically every object has that. So each object also has some unique identifier associated with it, an ID associated with it, kind of like every person with a social security number or every person who has a driver's license has a unique ID. The same thing is true for objects in Python. So for example, if I say I equal 100 and j equal I, and I compare those, they come true, they have the same value. But they'll also say, are j and I the same object? Are these just names that are referring to the same thing in memory? That will also return true. So there's a distinction there that we'll see in a second. But if I look at that, there's a function that's built in called ID, where I can actually get the ID number. Now, if you run this, write this code, and do that, you're probably going to get a different number, because this number roughly translates to where in memory that object is actually stored. It's not exactly the same as something like a pointer in C or C++, but it is a unique identifier that identifies that object and that object only. That's guaranteed to be unique. But if I say, what's the ID of I? Well, it's the same 100 object, integer object that's referred to as that one. And that is operator, it checks to see if the object IDs match, where the double equal operator that we've seen a lot of times previously compares the values in each. So in other words, if I say I equal 10 and j equal 10.0, if I say, hey, are those values the same? It'll say yes, they have the same value. 10 and 10.0 are the same value. But if I say is I is j, that returns a false because they're different objects. They have a different type. This one's an int type. That one is a float type. And that can be a little confusing sometimes with objects referring to the same thing. We'll look at that in a second. But let's actually switch over to the Python shell again for a second and take a quick look at that. Okay, so here we are back over here. So let's say I equal 10, j equal 10.0, and they say I equal j. It says true, but if I say is I the same as j, it says false. And the reason being that they have a different ID. So if I say what's the ID of I get that. If I say what's the ID of j, I get that. Notice they have completely different IDs associated with them. If I were to say, hey, if I were to say I plus equal 1, and then do the ID of I again, you'll notice that I've got a different number now. The reason being that to change the value, we had to make a new integer object that has a different value, now has 1 in it, or 11 in it instead of 10. And now it has a different ID because it's a different object. And that one that we were referring to, the 10 that we were referring to, the integer 10, that goes away. That's gone now. That object gets discarded by the Python interpreter. Maybe. It might recycle that later. Let's say if I do k equal 10, and let's look at the ID of k and see what we get. Okay, so it actually did not discard it. It kept it around and it recycled it. And we use that again. Now we're referring to that object again that we had earlier. Interesting. But that has to do with how the Python interpreter is managing its memory. So rather than unallocating it, it said, well, I'll keep it around. Maybe it'll come in useful later. And here when I said k equal 10, it said, I already have that object. I just point you at it. There it is. Okay. So there's, let's switch back to the presentation just for a few minutes here. Okay, so one example where it can get confusing, where we're talking about object references instead of talking about the objects being just kind of data containers, is an example like this. So here I have like list 1, and I make a list 10, 20, 30. And then list 2, I set equal to list 1. Now, if you're used to some other programming languages, you might think, well, this is just going to make a whole copy of this. So now I have 2 separate lists. List 1 with 10, 20, 30. List 2 also with 10, 20, 30, but they're completely separate. But there might be some surprising behavior that shows up here, because really list 1 and list 2 are just 2 different names pointing to the same single list in memory. So when I do list1.append 40, and then I say print list 2, I haven't touched list 2, should have still been 10, 20, 30, but it now has a 40 on the end because they were both pointing at the same space in memory. And that's that shows up in other programming languages as well, where you have two references that are, or two, in some cases, pointers that are both looking at the same data in memory. And we change that one data, it changes them for both. So you might say, note that this is not making a copy of this. And I've seen beginning Python programmers make a mistake like this and say, okay, I have this list of things. I don't want to mess up my original list, so I'll make a copy of it by doing something like this. List 2 equals list 1, and now I have a copy. But you don't. You just have two different names referring to the same object in memory. So the idea here is, how would you make a copy since that doesn't work? Well, one way to do it is to, like I have down here, list 2 equal list 1, and then we have the square brackets with a slice that goes from the beginning all the way up through the last element. That'll make a copy of the entire thing. So the slice operator always returns a new list that was a new list object created from the previous one. So this is actually creating a whole new copy of that other one. Now there's another way to do this as well that is a little more clear, and it works on things other than just lists. And that is, to make a copy of an object in Python, there's a module that helps us with that, called the copy module. So we can just import it, and here's my list, and then here's my list 2, and if I want that to be a copy of list 1, I can say copy.copy. Now, there is one gotcha here with using copy, and that is if your list contains other lists, or if you have a list that has other references inside of it to other things, then when you do a copy.copy, it just does kind of what's called a top level copy. It just copies all of the things at the top. So if there were other lists inside of here, other references, then those are going to get copied into the new list, but they're going to still have those same references to those other objects. So a way around that is there's this really cool function where it's been done for us that is copy.deepcopy. And what that does is it makes an entire duplicate of not just the top level list, but every other nested list or object or reference that's down inside of it. So this is like if you want a complete copy that's completely separate with no references pointing at the same data, then you can do copy.deepcopy, pass the reference to the object you want the copy of, and then you'll get that copy returned out that's an actual copy of the entire thing. So this can be useful, and you may have run into cases where you have seen bizarre behavior where I'm changing this here and it's changing it there, or I've deleted something here, but I made a copy and then deleted it in the copy too. Well, this is the kind of thing that you need to watch out for when you're doing it. Okay, there are also a few useful functions for dealing with objects in Python. One is type. We just saw that a second ago. Another one is dir, gives you a listing of all of the object attributes and methods, kind of like a big list of those. ID we saw as well, that returns the unique identifier for an object. And then vars, if you put vars of an object, that will give you a list of the variables that are in some instance of an object. And you can actually use this to know, hey, does this for example, does this object have an X? Does it have a Y? If it does, then I can render it. So you can use this for a thing called introspection, where you can write code that looks into the object and decides what attributes it has, what methods it has, and then maybe use those attributes if it has them. If it doesn't, ignore it. But this kind of stuff, there's some other things as well that we didn't talk about. I do want to look at the dir thing a little more carefully. So let me switch back over to the shell for just a second here and show you where that dir thing can be particularly useful. So for example, if I do a dir of, I don't know, let's use that variable that we had up there, j, which if you remember, j had 10.0 in it. Notice it shows us a list of all the things it has in there. So absolute value, add, bool, and all these things with the underscores surrounding the word, those are all kind of the built-in special names. But you'll notice there's a whole bunch of those things that are built in, but also it has hex, imaginary, real, is integer, from hex, as integer, ratio, conjugate. There's a bunch of stuff in there that we could use. Now, one of the places I use dir a lot is if I forget something that's in let's say a module. Here, let's import math. And we say, what are all the functions that are in math? Well, you could go to the internet and you could look that up. You could certainly find the documentation for that. We could also just do dir math, and it will show you all the functions that are in there. So there is a list of all of them. Notice arc cosine, arc sine, sine cosine, arctangent. There's arctangent 2, which we've used a lot. There's a factorial built in here. There's base logs of different bases. There's radians, there's degrees, exponents. There's a whole bunch of different stuff in here. Another example might be with random. Import random, dir random. Show me all the things that are in there. And there you can see all the things. There's randint, there's shuffle, there's random choice. You can mess with the seed. There's rand range. There's uniform, things we've used before. So a bunch of stuff in there that's useful, and we didn't have to go to documentation or anything to find that stuff. And there are a lot of cases where that dir can be useful, but one of the things you may have noticed is there's that doc string that came up with math. So you could also say, well, let's do that again. Let's look at the math one more time here. Underscore, underscore, doc, underscore, underscore. Now you can make your own doc strings, but this gives the code a way to access the documentation of the function itself. So if I were to say math dot doc, it says this module provides access to the mathematical functions defined by the C standard. So this is kind of a duplicate of all of the C type functions you'd have for a C language library. But it tells us that. But you could look at the doc string for individual functions as well. So for example, I could say math dot underscore underscore, or let's do math dot atan2 dot doc. And notice it tells us the doc string of that. And because all of those things, a doc string is a special thing in Python, you can add doc strings to your own functions in your own code very easily to add documentation to them. And one of the advantages of that is when you go to make documentation for your project, it's already built into the code. The code defines what it does. You don't have to make a separate like spreadsheet or Word document and write out all the stuff. You build it right into the code. And then there are tools that will go through your code and print out the entire documentation for something like an API. And you can, with Python, storing those as part of the objects and giving us the ability to add those things to it, you can make it so it just spiders through the whole thing, and here's all the documentation. And actually the Python documents themselves that you would read on the internet are partially created from those doc strings. Okay, let's go back to the presentation. Okay, and that brings us to the other topic that I want to get through today, and this shouldn't take too long. But the other topic I want to cover today is called inheritance. And what inheritance allows us to do is build a new class, which remember classes are like blueprints for objects, for creating objects. So inheritance allows us to build a new class based upon one that already exists. So it's, in other words, if you wanted to build a house, one way would be to start from scratch and draw all the blueprints from scratch. And then the other way would be to maybe take an existing design you already had and then look at what you need for this house and say, well, we need to have a garage added onto it, or we need to add, it's on a slope, so we need to change the way the bottom of it is. But you'd use an existing blueprint and then just build the new one off of that. And that's kind of what inheritance allows us to do. So in other words, it allows us to create a new class that can inherit all of the attributes and methods of the original, but if there are things that need to be changed, we could add additional attributes or override, remove existing attributes, or we could add new methods, take away methods, or change what those methods do. So let's look at an example. Is probably the easiest way to get your mind around that. So let's start off with this example for a deck of cards. So a deck of cards, if we wanted to make a class for that, we'd probably want to be able to have the deck, shuffle it, maybe draw a card from the top, maybe replace the card on the bottom. Those are the kinds of things that you would do to play a card game with a deck of cards. So you might think, well, the constructor, it creates all the cards, creates all 52 of them. Shuffle just randomizes it, mixes up the order. Draw removes one from the top. replace, we have to know which one we're replacing, but we replace, put it back in, we'll say at the bottom. And if we wanted to, we could add other methods like choose random card rather than taking it off the top, or we could have replace it somewhere in the middle if we wanted to. We could have return to default, like factory box, that turns it back, puts the order back how it comes in the box when you buy it. But the idea here is pretty straightforward in what we needed to do. This is what we wanted to do. So here's what the code would look like for that. Relatively simple object to define the class methods for. But for init, we say self.cards. We start off with an empty list, and we go through each suit, heart, diamond, spade, club, and then we go through each rank, 2 through 10, jack, queen, king, ace, and then we just add a card that's suit or rank plus suit. So what's going to be inside of our cards list is going to be 2H for 2 of hearts. For example, 7C, 7 of clubs. Q, D, queen of diamonds. A, S, ace of spades, and so forth. So if we were making a card game, like an online poker game, this might be the way that we would store that data behind the scenes. And we just append those to that thing. So when we're done with this, we will have 52 cards stored in this self.cards list. Now shuffle, the random module actually has a shuffle built in, so we can just give it a list. It'll shuffle them around. There's a draw that basically just says take the card off the top of the list. So self.cards.pop and 0 says get the one from the top and give that value. And I suppose we should return that here. Here, let me fix that real quick. I need to add a return here. Okay, so we get that card out, we return it, but it's been removed from our list, and then to replace it, we say what card we want to replace, and it just sticks it at the end of the list. So the first thing in the list is the top of the deck, the last thing in the list is the bottom. And now we have a deck of cards object that embodies that. Now, and that we could use that would work great. But let's imagine we're making an online game that's euchre. And if you've ever played euchre, it uses a limited deck of cards. In other words, it doesn't use all of the cards. It only uses 9, 10, jack, queen, king, and ace. And some varieties of it actually use 8 through ace. Some of them use 10 through ace. So there's some different varieties of it. But typically it's 9, 10, jack, queen, king, ace. And other than that one difference between a euchre deck and a normal deck, that's it. It just has fewer cards. It has some of them taken out. So we could create an entire new class and duplicate everything we did earlier. But why duplicate shuffle? Because shuffle works the same. Drawing a card works the same. Replacing one works the same. Why would we go through all the work of duplicating all that if we already have a deck of cards that works? We just need to have different cards in when it gets created at the beginning. So this would be a good example of where we'd want to use inheritance, because we already have a working class that works for our thing. We just want to make a subtle change to how it is when it gets the cards put in initially. So we're going to use inheritance for that. So inheritance, we're just going to place the name of the parent class in parentheses here where object would have gone. So this is saying that the euchre deck is inheriting from the deck. So in other words, it's going to get all of the attributes and all of the methods from the existing class deck. But notice we have this def __ init here. This says this is overriding the constructor of the original one. So as a reminder, the original looked like this. So we're going to get all of these things, but we're going to replace this one with a new constructor that now looks like this. And that's it. That's all we have to do is have this one thing, because we've inherited all of the other methods. We've inherited shuffle and draw and replace. We don't need to re-implement those here. We only need to change this. And this is called an overridden method because we've replaced the one in the original with a new version. All the other methods are untouched. All right, now there is one other thing you can do, and that is you could actually use the methods of the parent class. So imagine we wanted a normal deck, but we just wanted to add a couple things, add a couple attributes to it, or change it just very subtly without having to rewrite or override the whole thing. Well, if you think about the example of you want to play a card game, but it has to have the jokers in the deck. Well, that's like a normal deck of 52 plus 2 extra cards added in. Why rewrite the whole thing, creating the whole deck, when we can just say, hey, take the normal deck, let it do what it does, but then after that, let's add 2 additional cards into it. And again, this is another place where inheritance can help. So notice what I've done here. We take the Joker deck, which is built on a normal deck, and then in our constructor, we actually call the constructor of the parent object, the deck object, which comes in there. So that's going to make the all 52, and then after that, we then add on Joker 1 and Joker 2. So we have the normal deck get created here with the normal constructor, and then we added a couple things on. And this can be useful for a lot of things. For example, this could be useful for you want to add a little bit of functionality, not just on the constructor, but anything, where you say, okay, this is going to move, but not only is it going to move, but we're going to do a little bit of extra motion with this one, with this type of object. And so this allows us to call the original version of this constructor, but then do additional things. Or we could call the original version of another method and then do a little bit of extra stuff added on to that. And note that you could have made the Euchre deck this way as well. You could have said call the original deck, put everything in, and then just remove all of the things that are 2, 3, 4, 5, 6, 7, 8 from that. And that's it for the deck with the jokers in it. We call the original constructor, we added a little bit to it. And that can be done in any of the methods in our classes. All right, to finish up here, I want to tie this into how you would use this in games. And inheritance can be especially useful for creating games. So if you think about particle effects, some particles will fade out, some will get larger, they'll move more slowly, some will be affected by gravity, some won't. Some are like fire particles, and some fall like snow, and they have a little randomness to them. But that's a good case where you have a base particle class that basically just has X, Y position, and it moves, it renders, just like we did last class. But then we want to change how it moves a little bit. We want to change how it gets created at the beginning. What attributes does it have when it gets created? Or how does it render? What's it look like? This one's a circle. This one is rendered differently with little snowflakes or something like that. So that would be one case. Another example that you're probably familiar with is if you think about like a vehicle. So if you think about a game like Grand Theft Auto, there are a whole bunch of vehicles, but they have different attributes. They're like buses and trucks and cars, and then even amongst cars, there's like sports cars and old sedans. But that's a good case where you'd want to have something like a generic vehicle class, because they all kind of work the same and they all kind of do the same thing, and they all people can get into each of them and out of them and drive them, and they have a condition and they can be crashed into each other. So we want to kind of treat them in a generic way, but also trucks behave differently than cars and can do different things than cars, and motorcycles and work differently than the other things. Another example might be non-player characters. That non-player characters that are wizards will have a different set of capabilities and things they can do than those that are thieves or peasants or wanderers. And so you could have a basic non-player character class that then the specifics of the different classifications all inherit from the generic version, and then add on different behaviors and different things that they can do. Same thing with weapons, same thing with treasures or other items that you collect, same things with any item in the game. That you might have a generic game item that has a position in the world, but then obviously a chair, it has different capabilities and different things you can do with it than something like a cardboard box or a locker that you can store things in. So there's a whole lot of places where you can use inheritance to your advantage and reduce the amount of code you have to write rather than repeating stuff over and over and over again. You basically build a base class, and then inherit from that to make more specific classes, and then those can have inheritance off of them. There is something that we're not going to talk about today called multiple inheritance, where you can actually inherit from multiple parent classes. And essentially what you do is in the parentheses where we had like deck, you just list those things in order. But that allows you to do things like, for example, you might have a student class, you might have an athlete class, but then you might have a student athlete that has both game schedules to worry about, but a school schedule to worry about. So you can make like a student athlete class that inherits from both of those and gets both a school schedule and a game schedule, both points scored per game and grade point average. They would inherit both of those things from those two parent classes. We're not going to dig too far into multiple inheritance right now, but I do want to play with a little bit of code with inheritance, doing something graphical. So if you want to take a quick break, we can pause here and then take 5 minutes, use the restroom, come back. I just want to do a quick 10 minutes of coding some stuff to show inheritance in action. And it'll be something relatively simple to start with here. And then the next lab you're going to have is going to be playing with inheritance on particle effects. So you might want to follow along with the code that I create today. And hopefully, if you do, then that'll make that next lab much easier to get started on. So take a break, and then we'll get started on that code. Okay, well, we're back. Let's go ahead and write a little bit of code here that shows off, at least to some extent, how to do inheritance. And what we're going to do is, let me switch over to a Python window here. Let me get that set up first. All right, so let me switch the input. Oop. Okay, so here we are in our Python window, and I'm just going to put together some code here that demonstrates inheritance. So what I'm going to do, import the usual suspects. So Pygame, math, and random. Let's initialize Pygame. Let's make a display surface. So ds equal Pygame dot display. Set mode. I apologize for my bad typing. I'm kind of at a weird angle on where the laptop is. We'll just make it 800 by 600 as usual. And now we'll have our while loop, while true. And inside the loop, we'll pump the event queue. We'll get the keys. And then we'll check the keys and say if keys sub pygame.k underscore escape. Break out of the loop, bottom of the loop, pygame.display.update. And then after the loop, pygame.display.quit. Okay, so there's our basic loop. Let's go ahead and add the code to frame limit this to 120. So here, we usually do like FPS clock equal pygame.time.clock. And then inside of our loop, at the top, we'll just do an FPS clock.tick. At 120 hertz. All right, so now we've got our loop. Let's go and run that. We'll make sure it works. Oh, and I had a typo right off the bat. I'll fix that. This is why I test it as we go here. All right, so there's my window. I hit escape, it closes, everything's up and running. Now, what we're gonna do is we're gonna make a class for a little object that walks around on the screen. So I'm gonna make a class, I'm gonna call it Wanderer. And what the Wanderer is gonna do is I want it to essentially walk around on the screen and do stuff. So I'm going to give it just a few attributes here. I'll give it an x and a y. So we'll say self.x equal, and I'm going to go and just make these random. And we'll give it a random y value as well. So it has a location on the screen, and I'm going to keep this example really short because I just want to demonstrate the behavior of essentially, in this case, inheritance at work. So there's the basic attributes we need, just an x and a y. Let's go ahead and give it a color as well. And we'll just give this 3 components that are all between 100 and 255. So this will help us see what they look like in different spots on the screen. All right, so there's a random color. We're not letting any of the components get too low. But let's also now create a move method. And what I'm going to do for this move method is I'm just going to say self.x plus equal. And I'm going to do a random uniform. Let's do negative 2 to 2. So we'll generate a random value in that range, negative 2 to 2, and we'll just add it to x. So this thing will kind of wiggle around a little bit like that. And we'll do the same thing to y. And the other thing that I want to do here in the move is I want to make sure they don't leave the screen. So I'm going to say if self.x is ever less than 0, then self.x equals 0. And I'm going to do the same thing on if self.x is ever greater than 799 in this case, then set self.x equal to 799. So we're just capping it so it can't leave the screen. And then we'll do the same thing for y. So in other words, if y gets less than 0, then it's equal to 0. If y ever gets to be greater than 599, then set y equal to 599. All right, so there's move. Now let's make a render. So here, def render. So this is, we're just going to draw a circle. So pygame.draw.circle. And in this case, when we go to draw the circle, let's go and draw the circle on the display surface in self.color and at a position of int of self.x, int of self.y, and a radius. We'll just hard code the radius at, and let's do 8 and make the circle solid. Okay, so there we have the our base class. So let's make a list of these. So let's call this like a wanderer list. We'll make it empty. And now let's add some to this. So for I in range, let's make let's make 30 of these guys. And we'll say wanderer list.append. And what are we appending? We're just appending one of these wanderer objects. So we're going to make an instance of a wanderer. Now we have 30. So now what we're going to do down inside the loop down here is I'm just going to make a for loop and say for each one in the list, wander dot, in this case, wander dot, I'm going to do move. Is that what I called it? I think I called it move. Yeah. And wander dot render. So we move them all, each one in the list, we move it, we render it, we move it, re-render it. All right, let's run that and see if that actually works. Okay, there they are, kind of wandering around. And we're not doing a clear screen, so they're kind of leaving trails behind. So let's go ahead and add our clear screen to that up here. So display surface.fill, 0, 0, 0. And now they'll clear the screen, and now they'll kind of wander around. So notice they're kind of jiggling. Okay, now let's add some inheritance to this. So I'm going to make another class that's built off of this one, but I don't want to have to rewrite this whole thing. Essentially what I want to do is I want to make the class that builds off of this one essentially very similar to this, but I want to add the ability to teleport. So I'm going to make a teleporter, a wandering teleporter, essentially. So I'm going to make a new class, make it down here. Wandering teleporter. But now, instead of putting object in here, I'm going to put wanderer as the parent object. So notice if I just do that, that inherits everything from up there. But I want to make some changes to this. Specifically, I want to change how it moves. So I'm going to have def move, just like we have up there. But I don't want to completely rewrite all of this. I want to still move like it did before. I just want it to every so often pick a new location and spawn in a new spot. So in here, I'm going to go ahead and call the original one. So I'm going to call wanderer dot move self. So that calls the original one. And now I'm going to add my code that now teleports it. So I'm going to say if random dot rand int, and let's make this like a 1 or 0 and 1,000. So if that is equal to 0, we get it. So that's a 1 in 1,000 chance, essentially. I guess for it to be 1 in 1,000 chances would have to be 999. There's 1,000 possibilities. If it comes up 0, then we're going to pick a new random x and y. Well, we already have code that does random x and y up here, so I'm just going to kind of copy those two lines. And now we've had the teleportation. So it'll move normally by calling the original one up here, which does all the moving stuff. And then we say, you know what? But if there's a 1 in a 1,000 chance comes up, I'm going to locate to a new location. Now I'm also going to do something else down here. So we can tell these apart. I'm going to change the way they render too. So I'm going to say render. Now I could completely override this one up here to make these ones look different, or I could go ahead and call this one and then add on to it. So what I think I'm going to do for the teleporting ones is I'm just going to call this original one and add on to it. So it's going to be similar to what we did before. So wanderer dot render self. So just like we did with move, but now I'm going to add another circle onto that. So I'm going to make the teleporting ones. I will make them make a circle 2 pixels bigger, width of 1, so it's like a ring. And for color, I'm going to make the ring on all of those white. All right, so now the wandering teleporters are going to look different. So now if I just come down here, I could add some wanderers. Let me add 10 wandering teleporters to that as well. So for I in range 30 or 10, let's add them to that same list. So rather than having 2 separate lists, and this is a cool thing that we can do, since both of those have the same attributes, they just behave slightly differently. We can have add them to the same wanderer list and add 10 of the wanderers and add 10 of the wandering teleporters. And then down here, we go through and they all have a move, they all have a render. So let's see what happens. Okay, so now you can see, you can tell, here's a teleporter here, he's brown. Let's follow that guy and see how long it takes for him to teleport somewhere. You can see some of the other ones teleporting. Oh, there he goes. He jumped over here. So the wanderers still do what wanderers do. The wandering teleporters do what the wanderers do, but they have a little bit of extra functionality added on in the form of the thing. And if we wanted to, we could actually give them an additional attribute that says their teleportation rate. We could add a thing that's the size of the little circle around them. And we could add additional attributes the same way we added things to these. So we could call the original one to pick this stuff, but then we could add on to that other attributes if we wanted to. But you'll notice how that makes it a little bit easier because we only have to define what is different about this one than the original. So we didn't have to write any of the move code. We rewrite any of that or copy and paste that. We just used the move code from the parent, and then we did a little bit of extra work after that. Same thing with the renderer. We called the normal renderer, but then we added something after it to do that. So maybe you have a generic player class, and the wizard version adds a hat and a staff or something when it renders it. Who knows? But this gives you the idea, and if we wanted to, we can make, instead of wandering teleporters, we can make other ones that are some other type of thing that rather than teleporting, they move in a different way. So rather than wiggling around like these do, they pick a direction and stick with it until they run into into a wall. Or maybe we have some that pick a direction and a time and they walk that way for that time and then they change directions. They walk and they change directions, and they walk and they change directions. So we can make a whole bunch of different things. So you can kind of start to see, I kept this example very small and very simple on purpose to just show you kind of the power of inheritance and show it in practice. But you can imagine how you can make a game like Grand Theft Auto with a generic vehicle class for vehicles that move around and can be driven, and then you subclass off of that with these are trucks, these are sports cars, these are cars, and then you can subclass off of that. These are sedans, these are sports cars, these are convertibles, these are coupes. These are station wagons, these are SUVs, and then you could subclass off of those to the different manufacturers and the years, and add attributes to the different ones as necessary. If it's a convertible, what kind of top does it have? If it's and you can kind of see how you can build like a hierarchy of classes all using inheritance. Now, it's a little more confusing when you look at the code, because when you look at this code, you have to notice that this is inheriting from another class, which means that the attributes for this wandering teleporter aren't just listed here underneath it, they're also listed here. So it makes it, should be a little more careful. Okay, so let's go back to the presentation for just a second here. And that's all we're doing today. And so everybody stay safe, wear a mask. Next class, we're gonna have another lab doing some particle effect stuff with inheritance, kind of like what we looked at today. And I'll go over that in the next lecture and give you some time to work on that. But everybody wear a mask, wash your hands, stay safe, do your homework, make sure you get lab 1 done. And that's it for today.